Here in chapter 2, we're essentially going to look at math that is used for, it's related to pharmacology, so dimensional analysis. Our learning objectives is explaining what that actually is, talking about some different fractions and how to convert between them, looking at some different common fractions and variations of those, talking about ratios and proportions, Roman numerals and converting those, interpreting military time and converting to and from standard, talking about international units and milli equivalents, household and metric systems for numbering, converting Celsius to Fahrenheit and back and forth, factors that are related to calculating dose for somebody, and then looking at combining drugs and some of the issues with that and some of the terms associated with it. So dimensional analysis is just the process of understanding and applying qualities, so numbers essentially, of items based on their physical characteristics. So this includes comparisons of temperatures, weights, distances, so pretty much anything with a number or dimension to it. So surgical text and math. So it's important to understand the numbering system, also calculating dosage correctly, and just knowing some of the terms that go along with it. So first of all, looking at fractions. So we have common or simple, so these are the same thing, but you will likely see both terms used. So a common fraction and a simple fraction, this is where the numerator, which is the number on top, is over the denominator, which is the number on the bottom. So this is where the numerator is going to be smaller than the denominator. It can also be listed as a decimal. So this is just going to divide that numerator by the denominator. So if we take, for example, 1/2, so 1 is our numerator, 2 is our denominator. If we divide 1 by 2, we get 0.5. And then we can also convert those into percentages, which is a part of 100. So to do that, we're going to take that decimal we just did, divide the numerator by the denominator, and then we're going to apply by 100 to get a percent. So if we take 1 divided by 2, then that was at 0.5, and then multiply that by 100, now we get 50, but then it's important to remember that we include this percentage sign. It's a bad color there. So that percent sign is going to indicate that that number has now been multiplied by 100. So we're just moving the decimal essentially 2 places to the left. All right, so what is that decimal system? So Arabic numerals, so 0 to 9, just represented by a decimal. So that decimal point, which looks like the end of a sentence, a period, is spoken as point. So 0.5 is how that's interpreted. We always go from left to right. Whole numbers are everything that's to the left of the decimal. So if our decimal is here, everything that's going to the left of that decimal, that's called a whole number. So we have, ones, we have tens, we have hundreds, thousands, etc. Then everything to the right of that decimal is going to be a fraction. So it's part of a whole. So we have tenths, we have hundredths, and we have thousandths. Okay, so instead of tens, hundreds, thousands, we put the th at the end, indicating it's a part of that whole. So we add the tenth or thousandth. So again, everything to the left, whole number, everything to the right is a fraction. So some of the variations of common fractions. So again, a simple fraction is where the numerator, that top number, is smaller than the denominator. We can also have some kind of weird compound fractions, and this is where we have a combination of a whole number and a fraction. So we're compounding it. Then a mixed number is when we have a whole number and part of the fraction, so 2 1/4 is listed here. So we have that whole number and a fraction. A complex fraction is where we have a fraction. So here we have this mixed number 1 3/4. So we have this 3/4 fraction here that's actually part of a whole big fraction. We don't see this very often, but as we're going through them, we'll go ahead and give everybody their name. But again, a complex fraction is just a fraction inside of a fraction. Some more variations. So again, proper or common, same thing, just means that that numerator is smaller than the denominator. So 1/3, 1 again our numerator, 3 is our denominator, the numerator being smaller. Improper then is the opposite. So this is where we're going to have a numerator that's greater than the denominator, and it can be converted to a mixed number. So if we take 3 divided by 2, we get 1.5. So we get a whole number and a fraction, which is our mixed number. We also have equivalent fractions, which are just fractions that are equal, so they can be reduced or simplified by dividing them by a common number. So for example, 6/10, we can divide both of those numbers by 2. So if we divide 6 by 2, we get 3. And if we divide 10 by 2, we get 5. So 6/10 is the same thing as 3/5. Ratios are expressing a relationship between two numbers, using them to compare some type of comparison. So like 1 to 10 ratio, just meaning for every 1 of one thing, you have 10 of another. We see this a lot whenever we talk about people. So 1 out of 10, people will develop cancer or something like that. Always reduced to that simplest form. So if it's 5 out of 10, which is our ratio here, again, we can divide both of those numbers by 5. So we simplify it to 1 out of 2. So always reduce it or simplify it to its smallest. And then this can be expressed as a quotient, a fraction, or a decimal as well. All right, now proportions. So if we're doing proportions of things, so the terms of the ratios, we need to label those. So the terms must be stated kind of in the same sequence. Our known terms are on the left side of our proportion. Unknown terms are on the right side. And then we set it up as a fraction. We're going to cross multiply and then divide both sides by that same number. So what in the world is all of this talking about? So if we use the example over here, looking at ratios and proportions in like a word problem. So here we have Kelsey. She can read 4 sci-fi books in every 10 hours. So assuming that all the books are the same length, how many hours would it take for her to read 50 sci-fi books? So we have something that we know, we have a ratio we know, or proportion. So our ratio here is 4 and 10. So it takes 10 hours for every 4 books. So we're going to identify what we know and what we don't know. So our knowns, we know that she can read those 4 sci-fi books. We know it takes her 10 hours. And we also know that we're looking to see how many can be read, or how long it would take to read 50. So we know the number of books. What we don't know is how long that's going to take. So again, we put everything we know on the left side. So we have 4 books out of 10 hours. That's our ratio. 4 and 10. Okay, then that's going to equal those equivalent fractions. Our 50 books we also know, but we don't know how many hours. So we just use that as X. Now it's important that we use our units right. So we have books on top on both sides. So we wouldn't put X on top and 50 on the bottom, because now they're in reverse order. We have to make sure that everything is again equal. So those units have to be the same. So now this is where we're going to cross multiply and then divide. And all of that means is that we are going to cross these numbers. So we're going to take 4 times X, which gives us 4X. And then we're going to take 50 times 10. So we're making that cross multiplying. So that's going to equal 500, because 50 times 10 is 500. Then we need to get X by itself. So now we need to divide. So we're going to divide the left side by 4. That's going to give us X all by itself. And now we need to divide 500 by 4. So if we take 500 divided by 4, we get 125 hours. So it'll take her 125 hours to read 50 sci-fi books. Now, you're not going to need to know how to do that for word problems as far as books, but you would need to use it for determining the dose. So if we know we need to have 2 milligrams per milliliter of a drug or kilogram, and we know that the patient weighs X amount of kilograms, how much of the drug do we need to add? So those are calculations you'll need to be able to make using these same tools. All right, so then using some of the numbers and measurements. So if we look first at Roman numerals, so these are just symbols or letters that represent numbers. So we always read from left to right. The numbers to the right of the larger numbers we add. So we're going to use some examples here in a second. So if the number is on the right, we're going to add that value. So like xi equals 11, because we know over here, we have our little cheat sheet. You will need to know these 3. Okay, these are as high as we're going to get with surgery. The other ones are listed, like L is 50, C is 100. We're never going to use that big in Surg Tech, but you do need to know I equals 1, V equals 5, and X equals 10. You do need to know that conversion. So again, Roman numerals, we're using letters to represent numbers. I is 1, V is 5, X is 10. So if we see Xi that is listed here, how do we know what that number is? Okay, so we just read the rule. So the number to the right of the larger number, so 10, X is our larger number, so this I is to the right of it. So we are going to add 1 to 10, gives us 11. Okay, numbers of a lesser value to the left, we're going to subtract them. So now if we switch that, so now our larger number here, still X is 10, but now I is to the left of it. So we're going to subtract that number. So that's going to give us 9. So those numbers are those letters are the same, but the order matters. So we look at our largest letter that's representing that number, in this case, X is being 10. Our lower one is I, which is 1. So if it's on the right side, we add it to give us 11. If it's on the left, we subtract it to give us 9. Most of these can be repeated up to 3 times. So for example, or the exceptions are the bigger ones. Again, we're not dealing with those. But for example, we can have I, which is 3. But if we were representing 4, we would not say I. We wouldn't put 4 of them together. Instead, we would use that sequence. It would be IV, not intravenous. But again, V would be our 5. That's our larger number. If I is to the left, we would subtract it. That's how we would get 4 or represent 4 with Roman numerals. We wouldn't put 4 I's together. So again, our order of operations matters. We're going to subtract first and then add remaining values. Now, we're not going to have complicated, complex things, but if you're just interested in Roman numerals, for example, if we had IXV, for example, so now our largest number is X, but now what do we do with the I and the V? We have one on the left and one on the right. Well, we subtract first, so we do the left, and then we would add. All right, now looking at military time. So military time is what's used in clinical settings in hospitals, so it's important to become familiar with it. This uses a 24-hour clock instead of a 12-hour clock. So instead of 6 p.m. being 6 p.m., which is our 12-hour clock, we need to convert that to military time, which is 1800. So to do that, we're just going to add 12 to the hour if we're in the p.m. If we're in a.m., we're all good. So it's written as a 4-digit number, always. So 4 a.m., for example, is not just 400, it's 0, then the 400. So we always have those 4 digits. There's no colon between the hour and the number like we have in traditional 12-hour time. Take that colon out. And then hours are spoken only at the top of the hour, so when our minutes are 0. So for example, if it is 3 a.m., and we convert that into military time, 0, and then our 300, we say that. 0, 300, and then we say hours. Now, if it is 3:30, we would say, we don't say the 0. We would not say 0, 330 hours. We would just say 3:30 instead. Okay, so we're still going to say it with our hours, then our minutes. Even though there's no colon there to separate it, when we verbalize it, we say hours and then we say our minutes. We only say the 0 and hours if it's at the top of that. So we don't need to say 0, 3:30. Okay, we write the 0, but we don't say the 0 unless we're at the top of the hour. So again, if it's 3 o'clock or 2 o'clock or 1 o'clock, we say 0, 100 hours if it's 1 a.m. If it's 1:15, we write 0, 1, 15. Okay, we don't say 0, 1:15. We don't say 0, 1:15 hours. We don't say 1:15 hours. So again, just some of those understanding how to write it as well as how to say it is important. Now, a couple things that are unique to pharmacology. So these are units that we only use with pharmacology. International units, or IU, or units, is how these are represented. This is looking at biological potency. So how potent is a drug, meaning what's the lowest dose we can give for it to actually have an effect. So if it's a low dose with a big effect, like we see like with fentanyl and some of those narcotics, doesn't take very much to have a huge impact. It's very potent. Other drugs, we need to take a lot of it to get that same effect. So units, or IUs, represents how potent a drug is. There's not a conversion, so we can't convert that to like milligrams or milliliters or anything like that. It's just IUs, or units. That's the only thing that we're using it. We can't convert it to something else. So the number is written first, then we have a space, and then units. So there's a comma if we have 4 digits or greater for how it's being used. So for example, 3,245 IU. So we put a space there, then IU or units, either one is acceptable to indicate how potent a drug would be. Milliequivalents, this is represented as M lowercase EQ uppercase. So milli meaning 1,000, and then equivalents is again a unique unit. We cannot convert this. So like we have 1,000 milliliters equals a liter. We don't have 1,000 milliequivalents equaling something else. This is a unique measurement only for pharmacology. So it represents 1,000ths of a measure. And this is often referred to with electrolytes. So it doesn't, our electrolytes like our sodium and potassium, if you drink Gatorade or things like that, like Liquid IV, they have a lot of electrolytes in them. But electrolytes are available in super small amounts. And that number, that unit that is used to measure them, is a milliequivalent. Again, we cannot convert it to a milliliter, a milligram. It's milliequivalent. That's the only unit. A little bit about the apothecary system. We don't really use this. I stuck the slide in because your book talks about it, but not really something you'd be tested on. This is only used for a few medications like aspirin, codeine, digitalis, and phenobarbital. This is based on the weight of a single grain of wheat. So again, it's going way back to whenever apothecaries were being set up. Again, we're using more standard metric systems now. So weights are in drams, and we have fluid drams, which is again just measuring something based on how much a grain of wheat. Again, outdated system, but just a little history there for you, is called this apothecary system. We are most familiar with household or metric systems. The US kind of commonly uses household units. So things like inches, pounds, teaspoons, those are household units. These are more for our over-the-counter, or in some prescription drugs, we'll say, like 2 tablespoons or 2 teaspoons. Those are household measurements. These are limited though in the hospital. For the most part, you're never going to see these in a hospital setting. They're always going to use the metric system. So these are more, again, for things that don't need an exact measurement. Our metric system though, again, this is preferred in pharmacology and especially those hospital systems. All of the units in the metric system change by multiples of 10. Not the case with household. So if we're like converting inches to feet, it's 12. So we have 12 inches in a foot. Okay, we have, these like crazy conversion numbers that we all had to like memorize or learn in grade school. The metric system though is much simpler. Everything is just by tens. So we are increasing or decreasing by multiples of 10. So it makes that conversion a lot easier. Our base units are things like meters, grams, and liters. And then we can have like milliliters or centimeters, which are changing by those multiples of 10. So the unit always follows that number. We write out or abbreviate the prefix, again, like milligram. We have our little m that represents that, like we saw with the milli equivalents. We don't use zeros at the end of the decimal fraction. We just end with the last number. 1 milliliter is also equal to a cubic centimeter, so a cc. So this, again, preferred is just to use milliliter, but you do hear, and especially like on syringes, you'll see even sometimes they'll list cc. A cc and a milliliter are the same thing. So they are equal to each other. But again, it's best practice to use milliliter. But because some people may say I need 1 cc or 2 cc's, that's a milliliter. All right, now our temperature conversion, so going from Fahrenheit to Celsius, again, Celsius is what's used typically in the hospital setting. Fahrenheit, though, is more what we're familiar with. So from Fahrenheit to Celsius, we're going to take the number in degrees Fahrenheit, we're going to subtract by 32, and then whichever is easier for you. I listed both of them. I don't care if you use a ratio or the decimal, whatever is easiest for you. I prefer the decimals because it's easier to put in a calculator. But again, we're just going to subtract the degrees Fahrenheit by 32. And then if we're using the fraction, we divide by that fraction, the 1.8, or we multiply by the fraction. So if you're using 5/9, you're going to multiply by that. If you're using the decimal, you divide by it. All right. Going from Celsius to Fahrenheit, kind of the same numbers, but in a little different order. So we're going to take the Celsius, we're going to multiply by 9/5, then add the 32. Again, I prefer the decimal. So you take Celsius, multiply by the 1.8, and then add the 32. So pick whichever, don't learn both of them, just pick whichever one you can remember the best, either the 1.8 or the 5/9 or 9/5. And then learn it. So this is not something that would be given to you. You do need to know how to go from Fahrenheit to Celsius and vice versa without having the formula. Now looking at the dosage calculations, lots of things go into determining that. So how much somebody weighs, of course, would determine how much they're going to get. The therapeutic action of the drug. So what is it doing? So why are you using the drug? That can vary the dosing as well. Like if aspirin's being used as just like a prophylactic to help prevent a heart attack, it's a small dose. If it's being used to treat a headache or inflammation, it's a larger dose. So why are we using the drug? The patient's ability to metabolize. So is there something wrong with their liver? Do they have liver disease? Then they can't metabolize it, so that changes the dose. Are there any sensitivities or tolerance? So they're more sensitive to it or less sensitive. So if, especially with opiates, if they have a built-up tolerance, they may need a larger dose to get the same effect because they've developed that tolerance to it. Their age and gender or sex. As we get older, our metabolism slows down, so that impacts it. Younger, things are changing a lot, so that impacts it. Different genetic factors, and these are really hard to determine, but some different races, ethnicities will have some kind of, they're predisposed to having different conditions that need to be considered for that. Possible interactions with other drugs. So if somebody's already on a high blood pressure medicine, and you need to give them something else that impacts their heart, we need to adjust the dosage of both of those so that they're not going to kind of become toxic or have too much impact on the heart. The maximum dose that's allowed. So maybe they need a large dose, but that becomes toxic. So then we don't want to use that medication. How active are they? So again, that comes back to kind of the metabolism of the drug. The time even that the drug is given for some of them, that's not typically a consideration, but it can be. But also the route of administration. So is it being administered IV? So everything's going straight into the body. We don't need as big a dose as if it's oral and it has to go through the stomach and like not all of it gets absorbed. So that can impact it. And then what's called the hepatic first pass effect. We'll talk about this later in the semester too. But for oral medications, whenever drugs get to the stomach, there's what's called a hepatic portal vein. Takes everything absorbed from the stomach and it goes straight to the liver. Well, that's where drugs get metabolized. So drugs that are taken orally need a big dose because some of them aren't going to make it through the stomach to get absorbed into the blood. And then their first stop is right at the liver, where it's going to get metabolized and broken down. So what actually makes it into the majority of the body is really low compared to the dose that was given. So that impacts how much to give. And then any comorbid conditions like heart disease, liver disease, kidney disease, co meaning with, so other conditions that impact, especially again, our organs involved in metabolizing and eliminating the drug. When we are combining drugs, we have a few different terms that go along with this. So first of all, the drugs that are being added can either be synergistic or antagonistic. So synergistic, also agonist, can be used here, has the same effect. So for example, fentanyl and morphine are both pain relievers. So they're synergistic, which is why we wouldn't really combine them. But others can be antagonistic, meaning they have the opposite effect. So like a blood pressure medicine, one that's increasing blood pressure and one that's decreasing, those would have opposite effects. So anytime we're mixing or combining medications, we want to look for signs of incompatibility. So this can be visual or chemical, like it's bubbling, it's turning colors. It just doesn't look like everything is the way that it was before we mix them together. Those are things to look for. Is it being unstable? Is it, just doesn't last very long, or the changes are too extreme? But then we can also have therapeutic incompatibility. So it might look fine in the vial, but again, whenever we put those two together and they take those drugs together, it causes a reaction in the body. So again, something that's increasing and decreasing the blood pressure, that doesn't make sense to give those two together. They're not compatible when given at the same time. So that's a therapeutic incompatibility. So some of those safe practices whenever we're combining, so again, watching for that incompatibility, following the instructions. Again, most strict rule always applies, like we talked about in chapter 1. Consider the type of fluid in the IV bag. Is it going to have a reaction with like the plastic of the IV bag? Always apply sterile technique to prevent contamination. Be vigilant. Make sure you're reading and rereading that you're doing, giving the patient the right thing, mixing the right things together. Everything's accurately labeled. Label. Everything gets a label. And the dosage being correctly calculated when those drugs are being combined. So now a few terms that come with combining drugs. So reconstitution, again, most strict rule, use that sterile technique. The shelf life of some drugs may be limited. Especially if it's a liquid drug that needs to be given like in a syringe, but the drug is going to last a lot longer, have a longer shelf life if it's a solid. So it needs to be reconstituted. It comes in a solid form, but we need it to be a liquid. So again, how it's stored in that solid form is different than in the liquid form. So again, accurately label those medications, and then make sure you calculate the correct dose. So again, if that's solid drug and you're adding a liquid to it to reconstitute it, to get it back into a liquid form, make sure you're adding the right amount of fluid to it based on how much is in that vial. Make sure that dose is correct. Then concentrating or diluting medications. So to increase the concentration, just meaning we want more of the drug in that same amount of liquid, we're adding more solutes and less solution. If we need to dilute it, now we're going to add more of the solution, so less of the drug. So again, if we're increasing the concentration, we're putting more of the drug, less of the liquid. If we're diluting it, it means that we are adding more liquid to it so that we have less of the drug per milliliter of solution.